Hello there, Mr. Sutton here, bringing you the AP Calculus 412 Extra Practice Number 4 solutions on motion. For this one, for a positive or zero time, the velocity of a particle moving along the x-axis is given by this v of t function. We want to know at what time the direction of motion of the particle changes from right to left. So, in general, when your velocity is positive, you're moving to the right. When velocity is negative, you're moving to the left. So basically, we want to figure out when our velocity is changing from a positive quantity, a rightward quantity, to a negative quantity. So we can do this on the calculator. V of t changes from positive to negative at, well, let's go and find out. So here's my y equals. In y1, I've inputted this velocity function using x, because that's the input variable on a calculator. And I need a window to graph this in. Seeing as my answer choices are all clustered between, it looks like 0 and 3, if I round off, that's what I'll use for my window. So let me go to Window, 0 for x min, 3 for x max, and then zoom 0, to get a good picture of this. So there's my velocity function, and it looks like we're changing positive to negative right about here, near 2. Is it 2, though? I don't know. Let's do second trace and 0, and where's my spider? There he is. So let me click once to the left. Let me click the right bound here, and then enter one more time, and that gives me, yep, exactly 2. So there's the picture. This happens at time equals 2, so that would be answer choice C. For this problem, we're given the height of the object with the h of t function here, and we want to know the velocity of the object at time 3. Well, the velocity is just going to be the derivative of the height. So really, we're just trying to find v of 3, or h prime of 3, the derivative of height at time 3. And we can do that on the calculator. So here I am in the y equals of my calculator. Now, since I just need to find the derivative at a single spot, I don't actually need to know what this derivative looks like algebraically. I just need to put in the original function, which I've done here, and then take the derivative of that using the derivative function on my calculator. So let me quit out of this y equals, and we're going to do math 8 to pull up my derivative function here. We've got an x for the d there, and I'll do alpha trace to pull up my y menu. Y1 is where I stored the h of t function, so I'm taking the derivative of that. And then I'm going to do this at x equals 3. And press enter. Comes out to about 7.778, which gives us answer choice B. On this problem, this free response problem, we're talking about wind chill. This is how cold it feels in degrees Fahrenheit, and this is going to be a function of the wind velocity, which is in miles per hour. So if your air temperature is 32 degrees Fahrenheit, so this is only a very specific wind chill, then the wind chill, the new temperature, what you feel, is given by this w of v function right here. And this is valid apparently between 5 to 60. I guess if you're going faster than 60 miles an hour, you've got bigger problems than wind chill. So part A, we want to find w prime of 20 and then explain what that means in terms of the wind chill. So we can do this on the calculator. This is a calculator problem. Let me start by entering the original function here in my calculator. So I've entered this w of v function in my y equals, and I'm using x instead of v because x is the input my calculator understands. Now to take the derivative of this at 20, let me quit out of there, and I'm going to do math 8. That brings up my derivative function. Let me do dx. I'm going to do, let's see, alpha trace y1 for the function, because that's where I stored wv. And I'm going to do this at time 20, or velocity 20 actually. I like to say time, it's input 20. And that comes out to about negative 0.286. And what's that going to be in? Well, this is the change in wind chill, so this is going to be how the temperature is changing with respect to the speed. So this would be degrees Fahrenheit per mph. Now, what does this actually mean in the context of wind chill? Again, this is the rate at which our wind chill temperature is changing in degrees Fahrenheit per mile per hour at a velocity of 20 miles per hour. To put it another way, just in a little more plain English here, this is how much colder it's getting per increase in mile per hour when you're at 20 miles per hour. For this problem, this part, I want to find the average rate of change of W over the interval 5 to 60, and then find the value v at which the instantaneous rate of change of W equals the average rate of change. Okay, so we've got two steps we need to do here. First, they want us to find the AROC for W. So in general, that's going to be W of 60 minus W of 5, all over 60 minus 5. And let's see what that comes out to. So here we are back on the calculator. Now I've stored W in Y1 in part A. So I'm just doing basically W of 60 minus W of 5 up there. And pressing enter, comes out to about negative 0.254. I'm going to store that as a letter on the paper here. And let's see, what units is this going to be? Since this is the average rate of change of W, just like my units for part A, this is going to be degrees Fahrenheit per mile per hour. So there's my quantity I got on the calculator. Again, I'm going to store that as a constant A so I don't have to keep writing it. And on my calculator, I'm actually going to store that as well. So let me just press the stow button, and that stores my answer. And now let me just do alpha A. There we go. Okay. So we need to figure out basically where W prime of V equals this thing. That's what I need to do on the calculator. Before I can do that, though, I need to show for credit here what W prime of V looks like algebraically. I kind of put off figuring this out before because I didn't need it in part A, but in part B, if I'm going to solve an equation with W prime in it, I need to show what it is. So to do that, let's just go left to right and take the derivative. So 55.6, that's a constant. That derivative is just going to be 0. This next term, we can use the power rule. I mean, it looks weird with these decimals, but this really is just a variable to a constant. So I need, let's see, 22.1 times 0.16. Let me find that. 22.1 times 0.16 comes out to 3.536. So that's going to be the new coefficient, and that's going to be negative because we had a negative 22.1. Now we're going to have V to the what power? Well, that's going to be 0.16 minus 1. So that's going to be negative 0.84. And at this point, we've got something we can now set equal to my average rate of change, which again I represented with A, and solve this on the calculator. So back in my y equals, I'm defining y2 as basically W prime at this point. And again, I'm using x instead of v, but I've got essentially the same pattern. And now I actually need to define a y3 because I need to solve this equation. So I'm going to basically put each half of the equation in a y equals and then see where those lines intersect. So I need a in here, just a constant function of a. Let me just do alpha a. There we go. And one other thing, I don't want to graph the original function, so let me deselect y1. And now, what interval am I looking in? Well, they wanted to see where these things were equal on the interval of 5 to 60. So that's going to be my window that I'm going to go to here. It's kind of a weird window, but hey, 5 to 60. We'll just take what they give us. They know best. Let me do zoom 0 now. And let's see if we can see where these things cross. So there is my W prime function, and here's the horizontal line through A, which is about negative 0.25 and some change. So we see the intersection right there. Let me do second trace and option 5 intersect to see where that actually is. Let me arrow over here, enter 1, 2, 3 times, and that's about 23.011. And that's going to be miles per hour. That is the wind speed that gives you that average rate of change. For this last part of the problem, over the interval from 0 to 4 hours, they're telling us, the air temperature is a constant 32 degrees Fahrenheit, and at time 0, wind velocity is 20 miles per hour. If the wind velocity increases at a constant rate of 5 miles per hour, what's the rate of the change of the wind chill with respect to time at 3 hours? And they want units of measure. So basically, we've originally defined the wind chill in terms of the wind speed, the velocity, but now that velocity is changing, so we have to redefine this original function a little bit, and then we have to take the derivative of this thing with respect to time rather than velocity. Okay, so let me rewrite this. W of t, so a new function, W of t is going to be this 55.6 minus 22.1 times, and now instead of writing v, I'm going to write a function that gives me the velocity, so as a function of time. So we start at velocity 20 miles per hour at time 0, and then every hour we go up another 5 miles per hour. So if I wrote 20 plus 5t, then I'm increasing by 5 every single hour. So that's what I'm going to put in there, and I'm still going to have that exponent of 0.16. So this is my W of t function. What I'm going to do now is find the derivative of this thing with respect to time at exactly 3 hours. So I'm going to do this on the calculator. Now I'm going to try to be a little bit clever about this and save a little bit of time. Instead of rewriting this whole thing, I'm going to put the velocity function 20 plus 5x, I'll call this now, in y4. And back up here in y1 where I defined my original wind chill function, I'm going to replace this x variable up here with y4. So alpha trace, let me select y4. And now that's being raised to that original exponent with everything else that's happening. Let me quit out of there now, and let me delete all that. Let me do math 8 to get the derivative. So we've got derivative, and I'm going to do alpha trace y1 again, because that's my new and improved wind chill function now with respect to time, and that's going to be time 3 that we're plugging in, which comes out to about negative 0.892. And let's see, what units is that going to be? Well, this is wind chill with respect to time, so that would be degrees Fahrenheit per hour. On this no calculator free response problem, we have a particle moving along the x-axis for positive time values given by x of t equals this rational function. So based off of that, our first task is to show that the velocity of our particle is given by v of t equals this other rational function. All right, well, the very first thing we need to show, the most important thing arguably, is that velocity of time is really x prime of t. We need to show that connection or we're not going to get credit. So next, we need to actually take the derivative of x, which is going to require the quotient rule. So that would be u prime v minus uv prime over v squared. I don't need to write this, but I like writing it just to get an idea of where I'm putting things. To do the heavy lifting, though, I'm going to use my box and ribbon to organize this. So I have my u value, my numerator, which is going to be t squared minus 9. And then over here I have v, the denominator, 3t squared plus 8. Down here I've got u prime, which is going to be 2t. And over here this is v prime, so this is going to be 6t. Multiplying that back out, I'm going to have 2t times 3t squared plus 8 minus t squared minus 9 times 6t. All of that over, this is the v squared now, 3t squared plus 8 squared. And let's see, I need to simplify this so that I get 70t. So I can do that if I just multiply things out and distribute. So I've got 6t cubed plus 16t. And then over here, this is going to be negative 6t cubed. And then I've got a minus times 9 and a 6, so that's going to be plus 54t. The positive 6t cubed and the negative 6t cubed are going to cancel. And also, 16t plus 54t is going to be 70t. So there we are. On this part of the problem, they want to know if our particle is moving toward the origin or away at time 2 and give a reason. So this is going to be based on two things. We need to know two things. First off, is the particle to the left or the right of the origin, which is to say, is x of t negative or positive? And then, once we know that, is our particle moving left or right? Is x prime of t negative or positive? So let's find those two things and compare the signs of those two functions. Let's start with x of 2. We need to know where this thing is at time 2. So that's just plugging 2 into this function up here. So x of 2, we've got 2 squared minus 9 over 3 times 2 squared plus 8. And then evaluating this, we've got 4 minus 9 in the numerator, comes out to negative 5. And down here, this is going to be 3 times 4, so 12 plus 8, which is 20. This whole thing, I could reduce it, but really all I care about is the signage on this thing. So this comes out less than 0, negative. And that's telling me that my particle is to the left of the origin. All right, let's go ahead now and use x prime to figure out which way we're going. So we'll do x prime of 2 next. Recall that x prime, or v of t, either way you want to call it, is this function here, 70t over all this stuff. And they gave us this in part A. We just confirmed it. So then we're going to have 70 times 2 over 3 times 2 squared plus 8 squared. And let's see here. This is going to be 140 in the numerator. Down below, we've got 3 times 4, which is 12 again, plus 8 is 20. Square that, we get 400. In any case, positive over positive comes out positive. So we see here that our location is to the left of the origin, and we're moving to the right. That means logically we're moving toward the origin. Or if I want to be a little more rigorous about it, x of 2 and v of 2 have opposite signs. Therefore, we are moving toward the origin. On this one, the acceleration of our particle is given by this a of t function, which they're not telling us because they want us to find an expression for it, and then find the value of a of 2. So recall again from part A, our velocity is this function here. And to find acceleration, you need to take the derivative of velocity. And for that, we are going to need the quotient rule. So let me set up my box and ribbon. And in general, that's going to be u prime v minus uv prime over v squared. So we already did this once when we were finding v of t, or at least verifying it. Now we're going to do it again for a of t. So box and ribbon time again. We've got 70t, my numerator. And now we've got a little more complex of a denominator, 3t squared plus 8 quantity squared. Derivative of 70t is 70. Derivative of all this stuff, we're going to need a small chain rule. This is going to be 2 times all of this stuff times the derivative of 3t squared plus 8, which is 6t. And now for an expression, we've got big fraction. This is going to be 70 times this thing squared minus, I'm going to have 70 times, let's see, 70t times, this is going to, I'm going to call this 12t times 3t squared plus 8. And then down below we've got this thing squared again, so that's to the 4th power. So here's an expression for a of t. You don't need to simplify this. This is as good as you need to get. It's algebraically equivalent to whatever the simplified version would be. Let's keep going now. They want us to write and find the value of a of 2. So we basically have to plug 2 in for t for all of this stuff. So here's a of 2. Just all of this stuff, but I'm replacing all the t values, of which there's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, all of them with 2. It is your choice whether or not you simplify this. This is numerically equivalent to whatever the correct answer is. If you simplify it, you do it at your own risk. If you did want to simplify it, I'm not going to go through it. There's a whole bunch of arithmetic involved here, but eventually this will come out to negative 49 over 200, and you can verify that on your own, but either of these answers would be perfectly acceptable. On the last part of this problem, we want to know what position does the particle approach as t approaches infinity. So basically, we need to figure out the limit of the x of t function as t approaches infinity. So because we're approaching infinity, we're allowed to ignore slower growing terms, choose our champion, so to speak. So we can rewrite this function as the limit as t approaches infinity of t squared over 3t squared. And once we've done that, we can actually just cancel out those t squareds to get 1/3. For this problem, we have the number of gallons in a storage tank at time t modeled by this w of t function between 0 and 5. At what rate in gallons per minute is the amount of water in the tank changing at time t equals 3? So for this one, we already have the amount of gallons. We want to figure out the rate at which this is changing at 3. So we essentially need to do w prime of 3. Let's find w prime of t first. That's going to be minus 2t. And now we're just going to plug 3 into that, giving us a value of negative 6. And that's going to be negative 6 gallons per minute, which is choice D. For number 16, they're testing our knowledge of
what a prime actually means here, a derivative means. So on a certain day, total number of pieces of candy produced by a factory since it's opened is modeled by C, a differentiable function of the number of hours since the factory opened. We want to know the best interpretation of C prime of 3 equals 500. So C prime itself, that is the rate at which candy is produced, pieces of candy per hour. That's the rate at which the amount of candy is changing. So that means C prime of 3 equals 500 means that at 3 hours after opening, we are producing candy at a rate of 500 pieces of candy per hour. Let's see which answer choice most closely matches that. So choice A, factory produces 500 pieces of candy during its 3rd hour of operation. Well, that's not necessarily true. It's actually pretty close to what we said here, but this is saying during that whole 3rd hour. That's an interval of time. We don't know how much candy got produced during the 3rd hour. We just know that exactly 3 hours after opening, the rate of production is 500 pieces of candy per hour, the instantaneous rate. Choice B produces 500 pieces of candy during the first 3 hours. That's not even close. Again, that's an interval of time. Choice C, factories producing candy at a rate of 500 per hour 3 hours after opening. This is an exact time and a rate of change in the candy. So this is what we're looking for, choice C. Just taking a look at D, the rate at which the factory is producing candy is increasing at a rate of 500 per hour. So that's going one derivative too far. We're going to stay with choice C here. For number 9, this one's actually pretty tricky. We have a particle starting at rest from the point 2, 0, moving along the x-axis with a constant positive acceleration. We want to know which of the following could be the graph of the, pay close attention, distance of the particle from the origin as a function of t. So on all of these graphs, these are not positions of the particle. These are all graphs of the distance of the particle from the origin. So that means that the y-axis in all of these is not necessarily the y value of the particle. It is the distance from the origin. That's the output of all these functions. If we're starting at the point 2, 0, that means we are starting a distance of 2 away from the origin. So the output, 2, is a y value if you look at all of these functions. So our graph is going to have to start up 2 because you are 2 away from the origin at this initial point. So that means we're going to be looking at graphs A, E, and B. All right, so we have to do a little bit more digging. Now, they told us we had a constant positive acceleration. If we have a positive second derivative, that means that the original graph is going to have a concave up characteristic to it. Now, if we look at those choices that we had, A, B, and E, only A is concave up. And if you analyze it a little bit further, A is increasing at an increasing rate because we've got some acceleration going on. B is increasing, but at a constant rate, so there is no acceleration here. It's a 0 acceleration. Over here in choice E, we're not increasing at all, so definitely A is the way we're going to have to go here. For number 1, we've got a point moving on the x-axis with a velocity function of ln of t over t, and t has to be positive, or otherwise the ln function's not very happy. So we want to know where this reaches its maximum value. So for that, we need to figure out v prime and then find some critical values. So for v prime, we're going to need quotient rule. That'll be ln of t and t, if I use my box and ribbon here. Derivatives of those are going to be 1 over t and 1. Multiplying with my ribbon now, I've got 1 over t times t minus ln of t times 1 all over t squared. I can simplify this to just 1 minus ln of t, and I'm going to set that equal to 0 now and find some critical values. I'm now not worrying about 0 for a second, just things that make this undefined also count. So 0 is going to make this undefined both in the denominator and if you plug it into the ln up here. Now for critical values that make this 0, I need 1 minus ln of t to equal 0. So if I do 1 minus the ln of e, that would be 1 minus 1, which would give us 0. So e is also one of our critical values. Doing my number line now, this is going to have an endpoint of 0. I can't really test anything to the left of that because those values are undefined. We also have a critical value at e. Let me test out now 1. And when I'm testing them in this derivative here, t squared is always going to come out positive. So it's really just this numerator I have to test. 1 minus the ln of 1. Well, ln of 1 is just 0. So that's just a positive upstairs. And now number bigger than e, I'm going to go with e squared because that's easy to plug into the ln function, no pun intended. So 1 minus ln of e squared is really 1 minus 2, which is also negative. So taking a look at my sign analysis, my function doesn't exist prior to 0. And from 0 to e, we're increasing the whole time. And then we switch to a negative slope once we get to e. So that means since we're switching from positive to negative at e, I must have a maximum value at e, so choice C. For number 1, we have a particle moving along the x-axis, and the position on there is given by this x of t function over here, between 0 and 2, pi. We want to find the time for part A, at which the particle is furthest to the left. So furthest to the left, if we have a function telling us where we are on the x-axis, we're basically asking for the absolute minimum of the function, whether that's the most negative number or the least positive number, whichever is further left. So we're finding absolute minimum, which means that we're going to need to test out both the endpoints of the function into the function itself, and also any critical values for this function. To find the critical values, we're going to need to take the first derivative, and that's going to require us to use the product rule. So, setting up the box and ribbon for this, we have e to the negative t, sine of t, and their derivatives, negative e to the negative t, and cosine of t. Using our ribbon now to multiply those out, we've got negative e to the negative t times sine of t, plus e to the negative t cosine of t. Now we have to find critical values. So those are values that make this either undefined or 0. Since there's no values of t that are going to make this undefined, we're just setting this equal to 0 and solving. When we set it equal to 0, we can factor out a negative e to the negative t. That'll leave us with sine of t minus cosine of t inside our parentheses. And now we can set each of these things equal to 0. This negative e to the negative t term isn't going to really help us out much. There's no way to zero out an exponential function, so that's a dead end. For this next one, this one's a little bit tricky to solve if you've never solved this particular equation before. To do this, we're going to start by adding cosine to the other side. And then, this is one of the few times you can actually divide by something that has a variable. So in this case, we can divide because sine and cosine can't possibly both be 0 at the same time, because you're talking about the x and y value of something on a circle, the unit circle. And since neither of them can be 0, or since they can't both be 0, that means neither of them can be 0 because they're equal to each other. Any case, we can divide by cosine. That gives us tan of t equals 1. And then if we inverse tan that, we're just looking between 0 and 2 pi, so basically between 0 and 360 degrees. That's going to happen at 45 degrees and also positive 225 degrees. Those are the places where you have a slope of 1, where your tangent is 1. So in other words, pi over 4 and 5 pi over 4. So these are our two critical values. We're going to test these out along with the endpoints. Testing out our first endpoint, this exponential part's going to come out to 1. Sine of 0 is just 0, so that zeroes everything out. So that's our winner so far. Not a tough competition at this point. Let's plug in the first critical value now, pi over 4. So if we do that, we've got e to the negative pi over 4 times sine of pi over 4. Sine of pi over 4, sine of 45 degrees, that's radical 2 over 2. And this e is just going to move downstairs to go with the 2 that was already down there. Let's move on now to 5 pi over 4. So we're still going to move this e downstairs. Now it's going to have a positive 5 pi over 4 downstairs. This sine of 5 pi over 4 is going to give us, this is essentially the quadrant 3 version of 45 degrees. So this is, because it's below the x-axis, going to give us a negative value, negative root 2 over 2. So this comes out to negative root 2 over 2 times e to the 5 pi over 4. This is the only negative number so far out of all of these, so this is the winner so far. Let's try out 2 pi finally. So that's just going to be 0 because sine of 2 pi zeroes everything out. So given a choice between 0, a positive, and a negative, the negative is going to win every time. Since only t equals 5 pi over 4 results in a negative output, without even wondering what this is numerically, we know this is going to be the furthest left time. For part B of this problem, we're trying to find the value of a for which x of t satisfies this crazy equation here. So this is an equation that has a double derivative, a derivative, and the original function of x, all equaling 0. It's kind of intimidating at first glance, but you actually already have part of what you need here. I mean, you have the original function, x of t. They gave it to you up here. You also actually have x prime of t. You found that in part A, just rewriting what you already did in part A. It's this expression here. So now all we really need is this x double prime of t. Now that is a little bit of work. We've got two products if we take the derivative of this function. So I'm going to use two boxes and ribbons here. So for the first product, we've got negative e to the negative t and sine of t. So that's going to be positive e to the negative t and cosine of t. And I mean, if you think about it, this here is really just kind of the original function negative. So if you just reverse this whole expression, that's what all this is going to come out to. But if you didn't see that, you could use box and ribbon. Now I'm going to definitely use box and ribbon for this next part here. So we've got e to the negative t and cosine of t. So that's going to be negative e to the negative t and negative sine of t. And it's just a lot for me to try to keep track of. So if I put it here, I'm not going to forget things. Putting all that down here now, we've got e to the negative t sine of t minus e to the negative t cosine of t, plus, or actually minus now, e to the negative t cosine of t minus e to the negative t sine of t. See why I put this in the box? I mean, if I've got it here, I'm just doing my ribbon and writing things as I go. Otherwise, I'm trying to keep track of all this in my head, and I'm probably going to make some kind of mistake with these minuses here. All right, let's clean this up a little bit. This is kind of a mess, but we've got a positive and negative version of e to the negative sine of t. So those are going to cancel. And we have two of these negative e to the negative t cosine t terms. So that's negative 2, that stuff in the middle. And now we've also got, so this is the x double prime. So if we stick an a next to all of this and add it to this first derivative here, plus this original function, basically all of this, we've got the equation that they were looking for. So we had a times the double derivative. This part here was our single derivative, and this was our original function. Cleaning this up a little bit, it looks like we again have a negative and positive version of e to the negative t sine of t. So those are going to cancel. All that's left then is this first term with the a and this cosine term. We can go a little bit further, in fact. You'll notice that these both have a cosine of t and also an e to the negative t in them. If I factor out e to the negative t cosine t, I've got negative 2a plus, well, just 1 inside my parentheses. Now, solving this, we actually don't need to do anything with this stuff that we just factored out, because we don't care about t at all. All we care about is this a value. So if we just set this parentheses equal to 0 and solve, subtract 1, divide by negative 2, we get the a value of 1/2.